Hi. Now let's continue our study of measure theory. The theorem which I am going to prove today is a two-dimensional version of the theory on the density of local density of uh, uh, measurable sets. So let me recall you what it was in one-dimensional case. So it was a 1D theorem on the local density of L measurable sets. So it is the following theorem. Consider a set A, a set in R. A is Lebesgue measurable set. I remind you that Lebesgue measurable means it is a union of Lebesgue set, of a Borel set, and some set of outer measure zero. Yeah, so such sets are called Lebesgue measurable sets. So consider Lebesgue measurable set A, then for almost all the point B in R, the following is true. Consider the following limit. Uh, 1 over 2t measure, Lebesgue measure is denoted by lambda of the set B minus t, B plus t, intersection with A. And limit when t goes to 0. And this limit is for almost all B equal 1 if B in A, 0 if B is not in A. This was the theorem. Now, by some reasons, I would confess you that I love this theorem in its multidimensional version, simply because I use it in my work and I know that it's very good and powerful. And so I would like to explain now the, say, two-dimensional version of this theorem. Now, we have a set A in Lebesgue set of R2. Yeah, without restriction, we can consider a situation that A is a subset of a square 0, 1 times 0, 1. For example, because it trivially generalizes to a set in the whole plane. No, we can think about this set in the square. Then consider the following thing. Consider for any B, B1, B2, it is a point in R2. Yeah, and consider the square, which is O B T equals x equals x1, x2, such that model x1 minus b1 less than t, model x2 minus b2 less than t. It is the neighborhood. So we have point B. It is a square with center at B. It is a neighborhood, and usually when we are talking about open sets, the sets be such that together with any point it contains some disk with central this point of some radius. Yes, so instead of this we can take this square. Nothing changes. Yes, all the theory remains the same, but square is a more comfortable thing, more convenient. And then the theorem is that for any B in R2, for almost any B in R2, there exists limit of the following thing: 1 over 4t square. Lambda in this case is two-dimensional Lebesgue measure of the set x equals we have already O B T intersection with A when t goes to 0 is equal either 1 then B in A and 0 if B is not in A. Yeah. So this is what is in the denominator is the area of this square, and we see that it is called the density, Lebesgue density theorem. So any measurable set is at near almost every point of it is dense in sense that if you take smaller and smaller neighborhood, in this case it's square neighborhood of this point, then I would say percentage of the area occupied by the set goes to 1, goes to 100%. The proof is follows the same lines. Let me reproduce it here. No, first of all, outer measure. So how is the outer measure of set defined if the set is measurable set in the square? We consider the set A in, say, R2, and we consider the covering of this set by a countable set of these small squares. So we consider the O around the point B1, T1, union O B2, T2, union and so on. So we have a countable equals union from n from 1 to infinity O Bn Tn. So it is covering of our set. So it contains set A, and so A is subset of this, and consider the outer measure of A equals infimum of sum 4 T n square for all n from 1 to infinity, and infimum over the set O B n T n such that it contains A. Yeah. It is the area of this square. Now, this is more direct, definition of the measure, and we can define it as outer measure. So what is the difference between this notation, outer measure, and notation lambda? Outer measure can be defined for any set. For any set, it can be, say, any subset of a square can be covered by a countable number of the squares. Now, for example, it is all covered by one square where it is all situated. Yeah, and lambda relates only to Lebesgue measurable set. Yes, so it is elements, sets which are elements of sigma algebra. So therefore, we have different notations. So I don't write it this I would say outer measure equal lambda, and I write for a Lebesgue measurable set, lambda of A equals, by definition, outer measure of A. Now I can write this. No, for example, if you take any open set, open subset of, say, unit square, then its usual area is exactly what is written here. It is. I will leave it as a problem. No, instead of considering any set, let's consider the following thing. A equals x such that model x minus b square less than r square. So it is a disk of radius r around the point B. Proof that the outer measure of A equals pi r square. So we have to play with different coverings. I did not say that the covering of is no, it has written that the radius T n can go to 0. Yeah, so they should not be of equal radius. Okay. So how to prove this? I follow the same way, namely, I define the uh, uh, 2D maximal function. Two-dimensional maximal function. So what it is, if you have a function f of x, Lebesgue measurable function in say R2, yeah, so consider Lebesgue measurable function, then we consider the following function f star of b equals supremum over t integral over O b t model f of x d lambda of x, yeah, divided, I'm sorry, 1 over 4t square integral O bt model f x d lambda of x, yeah. So consider this. So it is the supremum of mean value of the function over the square. It is exactly parallel to definition in one dimension. Now we have another component. It is Markov or Chebyshev. In other book, in most of the books, especially in the probability theory, it is called Chebyshev inequality. That the measure of set x in R2 such that model x more than c less than 1 over c integral module f d lambda over r2. Yeah. The proof is the same. So it is the Chebyshev inequality. And what about the maximal function? The proof of maximal corresponding inequality, which is called Hardy-Little inequality for the maximal function, was based on the Vitali covering lemma. And in two dimensions, we have the following lemma. Vitali covering lemma in 2D. So suppose we have a set A in R2, and A is covered by countable, not more than countable number of the squares. A contains in union O Bn Tn say from 1 to infinity. So it is covered by countable set of the countable set of squares. This all. Then there exists a subset O B and K T and K, yeah, subset of this set of squares equals let me call them IK simply, I and K, and K, and it is equals union of IN, and from 1 to infinity. I define each each square I define by I, just like if it were a segment. So then there exists such that we have the following thing. First, I K intersection I and K intersection with I and J equal, so they don't intersect if K different from J. It is first. And second is the following. In one dimension, we consider tripled segment. And it was written that the union of tripled segments, I and K, contains union of IN. Yes? Here we have the following picture. We have this I and K, And to have the same factor, we have to add this. Let me draw this picture. This IMK. We have to consider all adjacent squares, and all in all, we have how to call it. It is tripled in both directions. So its area is 9. So we have to use that union of IN contained in union of 9 I and K. Yeah. And the idea of the proof is the same. First of all, we take I1. No, suppose that everything happens inside a unit square. I don't want to disperse myself to unnecessary details. Consider a unit square. Then all these squares are have the side no not more than 1. Yeah. Consider the largest square. Yeah. Now consider the next square. So I and 1 equals I1. So let's assume that from the beginning we arranged these squares in order of decreasing order of their sizes. Yeah, and I and 2 is the first square. Square in the sequence I2, I3, such that I and 2 has no intersection with I and 1. Yeah. No, if you cannot find, then we are done. But if you can find this I and 2, I and 3, I and 3, it is I the first sequence, the first square in the sequence, the same sequence, such that I and 3, I and 1, I and 3 intersect with I and 2. Yeah, and so on. And now either at some place, this process stops, so all further squares have intersection with one of previously chosen these squares, I and 1, I and 2, and so on. Either this happens or happens that we have an infinite sequence of these squares. But anyway, anyway, one moment. If say we have a square, so if IP is a square which is not in the list IN1, IN2, and so on, then IP intersect with I and K is not empty for some K less than P. So we have I and K, and here we have IP, this square, and this square IP, it is not fully included in I and K, but it will be for sure included in this inflated square 9 I and K. Yes, because its size less than the size of I and K, so it is enough space to absorb it. And that's it. And correspondingly, if you repeat the proof of the Hardy little wood inequality, we can have in 2D the following inequality. Hardy little wood inequality. The measure of the set F star more than C, less than 9 over C integral module F d lambda equals simply norm F in L1. 9 over C norm F in L1. So we have this inequality, and then we prove the following theorem. So we don't need it anymore. Following theorem. Suppose F Lebesgue measurable function. Let me write it in L1. No, let us do it in 0, 1 times 0, 1. So consider F in L1, and then for almost all B in 0, 1 times 0, 1, we have the following thing. Limit when t go to 0, 1 over 4 t square integral over O dt. It is the small square of size 2t. F of x d lambda of x equals f of d. Yeah. So the same theorem, but this time into d. Now the proof is also similar. We consider um, uh, we note consider one proof over 4t square integral over O bt f d lambda minus f of d, yeah, equals 1 over 4t square integral over O dt. Here f of x minus f of b d lambda. Yeah, because it is a constant. Integral this constant divided by the area of the square is exactly the value fb. Let me write model of this less or equal integral 1 over 4t square integral model fx minus fb over O dt d lambda. Now I swallowed other thing. I forgot to say that one of the lemmas here, which is proved also like it was done in one dimension with obvious changes, is the following lemma. If f in L1, then for any epsilon, there exists a function f epsilon such that f epsilon is continuous function, and norm f epsilon minus f 1 less than epsilon. So every function can be approximated by a continuous function in L2, L1 norm. It is one thing. Second thing, that if f were continuous, then the limit of this integral, of course, is divided by the area, of course, is 0. So we have only to consider the difference. And so 1 over 4t square integral over O bt model fx minus f of b d lambda less or equal 1 over 4t square integral over q bt model fx minus f epsilon of x plus model f epsilon of x minus f epsilon of b plus model f epsilon of b minus f of b d lambda. Okay, and now let me take epsilon equals 1 over n and call f 1 over n equals say hn of x. Yeah. No, to reduce to the same notations. So it is equal integral over 1 over 4t square integral o b t model f minus hn plus model hn minus of x minus hn of b plus model hn of b minus f of b d lambda. Yeah, no, just do shorter notation. And now we have the following thing. What is the measure where these how to estimate this the measure of the set where this integral is small. We know that f minus hn is norm f minus hn L1 equals 1 over n. And so the measure of set f minus hn more than c less than 1 over c norm f minus hn in 1. but f minus hn equals exactly 1n. Uh, uh, Equals no, or less or equal than 1 over c n. Yeah, uh, times yes, it is just small function. Uh, Now, about this, hn of x minus hn of b. Hn is a continuous function, so we don't touch it. Hn of b minus f of b. Mm, so, lambda uh, hn of b minus f of b more than c, less by the Chebyshev inequality. Uh, uh, no, one moment. I have already rolled this. Uh, so lambda of the following set 1 over 4t square integral module f x minus f h n of x d lambda uh, more than c. So it is the expression which enters the definition of the maximal function is less or equal uh, less or equal 9 over c norm uh, f minus hn in L1. Oh, equal f minus hn f minus hn in L1 equals less than 1 over n. So it is less or equal 9 over cn. Yeah. So we estimated the area where this is small. Now the measure of the set where hn of b minus f of b is small. It is simply because it is a constant. It is lambda uh, of b, uh, b. Uh, it is less than 1 over. So uh, this means that uh, after all, we have um, model 1 over 4t square integral model f uh, of x minus f of b. Uh, Let me start it. F x d lambda of x minus f of b less or equal one moment. So we have the estimate for the uh, measure of set where the integral of the first term is more than c. Yeah, it is this. Is less than 9 over cn. The measure of the uh, uh, set where the last integral of the last term is more than c is less than 1 over cn. Yeah, and consider the set b c n equals the set f of b minus hn of b less or equal model. Then C union of the set with the set uh, 1 over 40 square integral fx minus hn of x d lambda of x uh, less or equal than c. Yeah. So union of these two sets, it is defined by b, c, n, and we have uh, lambda of the set 0, 1 times 0, 1 uh, minus b, c, n less or equal, we have to take the sum of the measure of where this is not true, so it is given by this 1 over n, and where this is not true, it's 9 over 2n. 10 uh, uh, over Cn. Yeah, 10 over Cn. And now we consider any point uh, okay, uh, and consider B intersection B Cn. BC 2 to the power n. Yeah, consider this set, and then we have that uh, the measure of 0, 1 square uh, minus b lesser equal than sum of measure 0, 1 square minus b cn, which is less or equal 10 divided by c times 2 to the power n. Mm. Whew. No, we can take it uh, and from say j to infinity, then we have this. Yes. So we have this. So we take this set, and if b equals in the set B, then we have the following. It is not in any of the sets where then this integral is less than C. Yes, this is less than C. Then the following we have 1 over 4t square integral model fx minus f of b d lambda of x. X is in O B T. It is less than C, and here C to C plus I have to take care about this hn of x minus hn of b. But this is a continuous function. So if you take t sufficiently small, then the difference for this continuous function will be also less than c, plus 1 over 4t square integral over u bt module h n of x minus h n of b, yeah, d lambda of x. So this integral for a continuous function is goes to 0 because mean value of the function h of continuous function over small square goes to the value of the function at the center when the size of the square goes to 0. So it can be done less than c, less than 3c if t is small enough. Yeah. And now we can take j goes to infinity. Say for first we keep c constant, j goes to infinity, and have it that it's less than 3c. And then we take c also goes to 0. Yeah. So if we have for constant c, we have the following thing. If c is constant, then for all the points in the set B, the this difference is less than c, 3c. Yeah, first of all. Then first it holds true on the set of small measure. Yes, if j increases, then the measure goes to 0. And then on the same set, we have that it holds for any C. Yeah, so C now goes to 0. And then we have that the set where for sufficiently small t this does not hold, so for sufficiently small t this difference, what is the difference is f of b minus 1 over 4t square integral over O dt f of x d lambda of x, this thing. So the this inequality less than 3c holds almost everywhere for sufficiently small c. No, this means that it holds that the limit is 0, because we are on one and the same set of full measure. So it is the same proof, literally the same proof. The only thing is a little change in the Vitali covering lemma. No, that's it. And of course, it is possible to generalize this to any space dimension. So this great theorem holds true in any Rn for any n. Okay, let's finish for this, and next will be next. For now, have a good time. Bye. Yeah, I'm sorry. I wanted to add just a few words to what was done here. I was going to prove the density of almost all points of a measurable set in two-dimensional space, say in the square. But I did not finish it. So let us call density at the point B of the set A equals limit when t goes to 0 of the following thing, 1 over 4t square, measure of A intersection with O, B, T. Yeah, T goes in degrees in a square. So it is the mean, say, content of the set A in a small square, and limit when the size of the square goes to 0. And I showed how to prove that limit 1 over 4t square t goes to 0, integral over O b t f of x d lambda of x equals f of b for almost all b, 0, 1 square. So what remains to be said that dB, I would say, measure of A intersection with OBT equals nothing but integral over OBT, characteristic function of the set A of x, d lambda of x. Yeah, so it is also a measurable function, and so this is dB of A equals limit when t goes to 0, 1 over 4t squared integral over OBT, characteristic function of the set A of x, d lambda of x. Yeah, and equals for almost all b, it is equal to 1 if b in A, 0 if b is not in A. That's it. Now I'm really finished. I just forgot to make this last stroke. So now it's finished. Bye.